We spent the last couple of days talking about curved mirrors. Before that, you'll remember we talked about curved lenses, which are applications of refraction. Refraction is the bending of light. When light goes from one medium to the other, the speed changes. And because the speed changes, the wavelength and the angle also change. Okay, refraction, the bending of light. Now we're going to talk about diffraction, which is not the bending of light at all, but rather the spreading out of light, or generally the spreading out of a wave, specifically for us, the spreading out of light. Here's a photograph of actual diffraction taking place with water waves. The same thing would happen with light waves. It's just easier to see with water waves because light waves need to reflect off of something to be visible. When water waves or when light waves encounter an opening, they will go through that opening, but as they do, they don't bend. They spread out like this. That's diffraction. The amount of diffraction depends upon the size of the opening, depends upon the frequency. We're not going to panic about that here. We just want to remember what diffraction means, the spreading out of a wave when it goes from one medium to another. Now, what happens if we have two openings? If we have two openings, then we get diffraction taking place from both of those openings. Let me draw a little picture by hand here. Here's my two openings. Here's my water waves or whatever, light waves, whatever it is, going towards the two openings. Right, Logan? Going through those two openings, both of them will diffract. Both of them will spread out like this. We get a diffraction pattern for each of them individually that looks essentially like this. But because there's two diffraction patterns, at some point they're probably going to overlap. And where they overlap, we get interference. You'll remember from Physics 20, interference is when one wave hits another wave and produces either a bigger or a smaller wave. When two crests hit each other or two troughs hit each other, you get a bigger crest or trough. That's constructive interference. When a crest and a trough hit each other, they make a smaller wave, which is destructive interference. Here's two openings. We have an opening right here, and we have another opening right here, which we can't really see because the guy's head's in the way. Both of those are producing diffraction patterns like this, but as the diffraction patterns overlap with each other, we get an interference pattern as well. The interference pattern looks like this as water waves, where we have an area you can see right here of bigger crests and bigger troughs, constructive interference. We also have an area of constructive interference here and here and here and here. Now, in between those areas, you have areas of destructive interference. You can see those calm areas where there is no wave, where crest and trough met each other and canceled each other out. Destructive interference. So we have alternating lines of constructive and destructive interference. The constructive interference lines we call antinodal lines, destructive we call nodal lines. The same thing will happen with light or any kind of EMR. The problem is if we're using light or EMR, we can't see what we see with water waves. In order to see light, it has to reflect off of something. When light goes through the air, you don't see it. The activity that you did with refraction here last week, you shone the laser light through the block of glass, right? You know that the laser light was not visible in the air between the laser and the block of glass because it wasn't reflecting off of something. There would be this interference pattern produced with laser light if it went through an opening here and here, but you wouldn't see it because it's not reflecting off of something. So, how do you see it? Well, let's put a screen there. If we put a screen at the other side, this picture that you see on the board right now you see my light waves coming down this way. We have my two openings. They're diffracting. They're overlapping, and as a result of that overlapping, they're interfering. And as they interfere, they produce those antinodal lines or lines of constructive interference. And they produce those nodal lines or those areas of destructive interference. We can't see them, right? Because the light's not reflecting off of anything. They're there, just like the water waves are there, but we can't see them unless we put a screen right here. If we put a screen right here, then we do observe the areas of constructive and destructive interference, but we observe them a little bit differently. Constructive interference appears on the screen as a bright spot. Okay, right there, a bright spot. And then the next constructive interference appears as another bright spot. But the area of destructive interference in between the bright spot and bright spot is what we call a dark spot. And notice I'm using quotation marks for that, a dark spot. I don't mean necessarily black. I mean the absence of bright. Does that make sense? If I shine it on the whiteboard up here, you're not going to see red, black, and red. You're going to see red, absence of red, red. Or red and whatever the background is, red. Does that make sense? So we say bright spot, dark spot, but it's really bright spot, absence of bright spot, absence of bright spot. Now, we've been calling this red spot a bright spot. We could also call it a maximum. A bright spot is a maximum. We could also call it an antinode. Bright spot, dark spot, antinode. We talk about our physics thesaurus. Bright spot means maximum. Bright spot means antinode. Versus our dark spot. I'll put that in quotation marks because, as you know, it's not really darkness. It's just the absence of bright spot. Our dark spot could be called a minimum because it's minimum light. Can't spell it right, but you know what I mean. It also could be called a node. So any of those terms mean exactly the same thing. If you see one, just associate it with the others. Now, if I look at my screen, I see this, right? Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. Okay, this is what I actually physically see, what you see I have in red down here at the bottom of the screen. But if I was to plot a graph of what I see, not a physical photo of what I see, but a graph of what I see, that graph representing intensity of the light versus position, then the graph that's up on the board right now is what I would get. You can see that in the middle, where we have our central maximum, or our central bright spot, or our central antinode, our middle bright spot, you would have high intensity. Then right beside that, you would have a minimum, or a node, or a dark spot, where we would have zero intensity. And then beside that, we'd say we'd have our first order maximum, first order bright spot, first order antinode, where you have high intensity again. And then a minimum, and then the second order maximum, where you have higher intensity. And then on the other side, we have our middle, and then on the left side, we have the same thing. A first order maximum, a second order maximum, and so on and so on and so on. We just haven't drawn them all. Now, this is a confusing looking diagram. Let me explain it because it's not really nearly as bad as it looks here. Okay, look at the left-hand side. We have light, which is monochromatic. You guys remember what that means, right? Monochromatic light is one color, yeah, one color. It's shining on these two openings, and of course that monochromatic light, as it goes through those openings, diffracts like this, spreads out. But of course, those diffraction patterns end up overlapping, and as they overlap, we get an interference pattern. That interference pattern has antinode or bright line or maximum, dark line, bright line, dark, and so on. Right? But we can't see those because the light's not reflecting off of anything. So we put a screen down here, and when we put a screen down here, this is what we see. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. This would be our central antinode, or central bright spot, or central maximum. Next one would be our first minimum, first order maximum, second minimum, second order maximum, and so on. Second order maximum, second order antinode, second order bright spot, whatever you want to call it. We can describe what happens here. We can describe the position of these antinodes, the angles involved, distances involved, and so on by two equations. And those two equations are written on the board right now. Lambda is equal to d sine theta over n. Lambda is equal to xd over n times L. Now, there's a big if right here that we'll talk about later on, not right now. Assume right now that it's just always good. But we do have to recognize what each of these variables mean, and they are a little bit more confusing than a simple equation like v equals d over t. Let's identify the easiest one first. Lambda represents wavelength, and we typically want to be in meters here. In either equation, lambda is the wavelength of the EMR in meters. So again, if we're talking about monochromatic light, red light, let's say, 10 to the minus 7 meters, that's what we're talking about here for lambda. D, little d, in both equations represents the distance between the slits. And that's going to be measured in meters as well. This is a little d right here, the distance between the slits. That's going to be a small number. Okay, Rachel saw when I showed her the diffraction grating that we used in our little demonstration here, she saw that those two slits were really, really close together. So that little d value is going to be a small number, especially when you record it in meters, it's going to be a small number. L, which only appears in the one equation, represents the distance from the slits to the screen. Now, I made that a capital L over here. It's a lowercase l in the equation. Doesn't really matter what you make it. I just didn't want to make it a lowercase l over there because it looks like a 1, right? I made it a capital L so that you can tell that it's supposed to be L versus the number 1. So we're going to say that's the distance between the slits and the screen. And what do you think we're going to measure that in? Meters, of course. Now, what I'm about to show you is going to look a little bit confusing. So bear with me on this, okay? I'm going to say that X is going to represent the distance from one maximum or minimum to another maximum or minimum. From one to another. Which one to which one? From any of them to any of them. Let me show you what I mean by that. This value, this can be X. This could be X. This could be X. This could be X. From any maximum or minimum to any other maximum or minimum. So how is it that we're going to get the same answer if Joshua has X going from first to the second, but then John has X going from the central maximum to the second? How can they both get the same answer? Yep. N. Yeah, exactly. N has got to be consistent with it. So whatever you use for X, that's fine, as long as your value of N is consistent with it. N is the difference in the maximum number. So here, if X is that distance from 1 to 2, N would, for that one would be 1. 2 minus 1 is 1. Here we'd say N, since we're going from 0 to 2, would be 2. 2 minus 0 is 2. Here we'd say N, we're going from 1 on the one side to 2 on the other side, N would be equal to 3. 2 minus 1 is 3. This one's a little bit trickier. What do you think this one is? We're going from the first order minimum or dark spot or node to the second order antinode. Yeah? Good. N would be 1.5 there. Right? We consider that to be 0.5 to 2 gives me 2 minus 0.5 is 1.5. So if John used this one, that's fine as long as he makes N2. If Joshua used this one, that would be fine as long as it makes n 1. Somebody had a question there? Yep. You're good? Okay. Now the only, no, n wouldn't be 0, no. No. It's the minimum value of n would be 0.5, and there wouldn't be a maximum value. All right, one more variable here, theta. Theta, of course, represents an angle, right? But what angle are we talking about here? The angle from the central maximum, always from the central, to the first order maximum, or it could be to the second order maximum, or it could be to the third order minimum. It can be from the central maximum to whatever you want. X is a little bit more general, a little bit more open, because X can be measured from anything to anything as long as n is consistent with it. Theta can be measured to whatever you want, but it has to be measured from the central maximum. You got to have the same starting point with theta, always from the central. And again, you got to make n consistent with that. So in this case, we'd make n 1 because we're going from 0 to 1. In this case, we'd make n 2 because we're going from the central maximum to the second order maximum. If we went to the second order minimum, n would be 1.5. 1.5 minus 0 is 1.5. Now, one more little thing before we actually put this into practice with some calculations here, all right? We started off this page by establishing that we had monochromatic light, one color of light. Usually it's red, because most lasers are red light. Okay? At least commonly available lasers are red light. You can get different colors, but most of them are going to be red. If we have red light, then we get this pattern where all of these maxima, or bright spots, that are formed on the screen are red. If we happen to use green, then we would get all of these maxima that were green, right? But if we're using something a laser that was blue, then we get all of these bright spots that were blue. But the blue bright spots would not appear in the same place as the red light spots. If we have red light shining upon this, we would get an interference pattern that looks like this. Let's just draw it as single lines here. We got a red line, 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 and so on. This would be our central bright spot, our first order, our second order, our third order, and so on. If we had blue, then we would get something that looked like this. Notice the blues are in slightly different positions than the reds. If you look at my picture of the dark side of the moon over here, by Pink Floyd, my 137th favorite band of all time, 136 spots behind U2, you see that red light refracts the least. Red light diffracts the most. Do you see that? Red light spreads out the most. It bends the least, but it spreads out the most. You can see that the red maxima are further away from the central than the blue ones are. Okay, so if I use red, this is what I get. If I use blue, this is what I get. What if I had red and blue at the same time? What would you see? You would see red and blue together right here, and then you would see a distinct red line and a distinct blue line. That's what you'd see. This would still be our first order maximum and our second order maximum and third. We wouldn't say 1, 2, 3, 4. Okay, both of those would correspond to our first order maximum. Both of those would correspond to our second order maximum. What would you see if you had all the colors of the rainbow? Well, you would see red, orange, yellow, green, blue, indigo, and violet right there. In other words, you'd see white right there. And then you would see right here for the first order maximum, not Roy G. Biv, but Vibgyor, the opposite of Roy G. Biv. The opposite, because we don't see red light diffracting the least like it refracts, rather it diffracts the most. It's the opposite of the spectrum. Does that make sense? So what happens if you get a problem? What happens if you get a problem where you have to solve for something, wavelength, D, theta, N, whatever, and you've got polychromatic light, not monochromatic light? Here's what I want you to do. Pick a color. If you have multiple colors, pick a color. Like, let's say we have data about blue. You've got all these colors, but you've got data specifically about blue. Pretend that there is no red. Just pretend it's not there. If you've got 6 different colors and you've got data about yellow, pretend the other 5 aren't there. Just pretend that only yellow is there and do the question the same as you would do the question if it was just red back here. Does that make sense? Don't get confused by polychromatic light. It looks confusing because you see all these different colors on your spectrum, right? But just forget about them all, except for the one color for which you have data. Okay, I want to do one example. Oh, sorry, show you this picture here first, and then we'll do an example. Don't worry about writing this down. This picture just represents if we have individually red, orange, yellow, green, and blue light. Okay, individually, we'd see that this would be our central maximum right here, 0. This would be 1. This would be 2, 1, 2, and so on. You can see that the blue central maximum, 1, 2, you can see the blue ones are closer to the central maximum than the red ones. That's because blue light diffracted the least, red light diffracted the most. Now, the reality is, because we have all these different colors, it doesn't end up forming a pattern quite as neat as this if they were all together. It ends up forming a pattern kind of like this, because you end up getting, say, the blue light from maximum 3 overlapping with the red light from maximum 2. So you get different spectra, but it ends up looking kind of, especially as you go further out, kind of just a hodgepodge of colors, it seems. Okay, let's take a look at an example, and then we'll wrap it up for the day here, okay? This is from your textbook as well. Page 689, question 3.8. It says monochromatic light, or one color. Although it doesn't really matter, right? If we had polychromatic light, all we'd have to do is look at one color specifically of the multiple colors. Monochromatic light is incident on 2 slits separated by this distance. Okay, that's little d, 0.30 millimeters, which I actually don't want to be in millimeters, so I'm going to convert that to meters by multiplying it by 10 to the minus 3. I can move the decimal place over, but I don't like doing that, so I'm just going to tack on a 10 to the minus 3. My angle, theta, is 0.080 degrees, and that theta has to be measured from the central maximum to some other maximum. Here we're talking about the first antinode. What would n be there? 1 minus 0 is 1. Looking for the wavelength here. Let's use the first equation, the one that didn't have the big if beside it. D sine theta over n. D is 0.30 times 10 to the minus 3. Theta is 0.080. N is 1. Do this. We get 0.3 times 10 to the minus 3 times sine. Sorry, that's not 0.080, it's sine of 0.080. And we divide that by 1, we get 4.2 times 10 to the minus 7. That's the wavelength of the light that was used here. If it was polychromatic light, well, then that would be the wavelength of the one that corresponded to that angle. If we had a slightly different angle, it would correspond to a slightly different wavelength. So remember here, besides all the variables and the equations and so on, remember, with refraction, red light or small frequencies refract the least. High frequencies or blue light refracts the most. With diffraction, it's the other way around. red light or low frequencies diffract the most. Blue light or high frequencies diffract the least. So with refraction, you get Roy G. Biv. With diffraction interference, you get Viv G. Orr. All right. You got a couple questions here that I'd like you to work on page 689 in class for the next 6 or 7 minutes. If you don't finish those, then finish them up for Monday, please. We're not going to go over them tomorrow in class. Just finish those up for Monday, please.